So I'm the guy that's standing in between you and break, and we're at the low blood sugar portion of the afternoon, so I'm going to try to be a lot more animated for myself and for you to keep things moving along here and keep everyone awake. So first thing, thanks so much to my dear friends, Patrick Hogan and Friedman. Friedman, thanks so much for giving me the opportunity to speak today, and the collaboration with these guys is actually what I'm talking about, and along with the cast of thousands that you're about to see. So as Friedman mentioned, I'm a researcher at Stanford. I've been there for quite a while, 15 years. Before that, NASA Ames, and the technologies that you're seeing are actually spun out of NASA Ames and Stanford. So coming back home again. So I'm going to jump us back up to 100,000 feet and try to give us a perspective across everything that you've seen this morning. So I'm a good cleanup batter at the end of the sequence. So just going in, and I thank Friedman for letting me steal some of the slides he's about to see that I stole. Talking about the big picture. So this is all the earthquakes that have happened since 1898 by magnitude. This was actually, I think, from Nature. As you know, I'm preaching to the converted here. The earthquakes are a very large problem worldwide. This is the sort of magnitude, putting some quantitation on it, some numbers. My screen's off a little bit. But you know the figures probably at least as well as I do about the impact on humankind. Here's the thing that we need to keep in mind, however, is that the impact is getting a lot worse. As we have greater populations on coastlines in major cities, the impact on humankind can be a lot larger, both in terms of mortality as well as economic loss will continue to increase. So earthquakes is a problem that we have always had, but its impact is even going to be increasing into the future. Okay, let's talk about earthquakes a little bit and how it compares to other known events. And again, I won't read the slide, but it is pretty interesting to see that you look at things like the largest hydrogen bomb in the world is at the low end of the scale. Going up from that, we have the other March 2011 Japanese earthquake, all the way up to 1960 in Chile. All of the world's nuclear weapons, if exploded, would only equal a little bit above what 1906 earthquake in San Francisco did. So a tremendous amount of power is released. So as you've seen with some of the talks today, with that much power about to be released, there may be some things that precede that as that power builds up and as capacitance increases. So if earthquakes are the deadliest of all natural disasters, what can we really do about it? And you've seen a bunch of different ideas here this morning, but I'm going to try to give a more integrative approach. Well, what if we were to collaborate and work together to solve earthquakes? What I'm talking about right now is a collaboration from a bunch of different partners that you see on the screen. NASA, European Union, government, academia, and industry working together with non-profits, and also anyone else in an open collaboration. Because what at least I've been impressed with is this morning is all of the great science that I hear across all of these different talks. People looking at physiological events, precursors to earthquakes, all the way to magnetic disturbances, every different way that you can possibly look at it. There's precursors that people have talked about. What if we were able to work together and really make a multiplied sort of impact on the world? So what I'm talking about now is, what if we were able to collaborate and work together to solve this problem together? So just to, again, preach to the converted about this a little bit, how are we going to solve this? Well, you know, we know about the tectonic activity and we know about the internals within our own planet. And again, I thank whoever I stole these PowerPoints from for the nice graphics. But basically, there are lots of precursors that are happening, and we can all look at what we believe may be going on underground that may be producing this. But to just summarize all this, deep in the earth, as rocks are squeezed, they produce electricity, they produce effects, they produce something that we may be able to measure. Okay. So here are just some of the measurable effects, many of which have been talked about today. ULF emissions, unipolar pulses we were talking about, air ionization, and then being able to pick up that air ionization either from infrared signatures or from lots of other things, from tree potentials, for example, from the last talk. So there are a bunch of precursors that happen that we could find indicators for. Okay, so just showing this a little bit more graphically, as I think Friedman mentioned earlier, you know, future hypocenter, upward ion current, lots of different things happen in the upper atmosphere that we might be able to detect, as well as underground. So this is one of my favorite slides because it really hits on all of them. We might be able to pick up a lot of these precursors, especially with respect to air ionization, through ground ELF pulses, ions, air ionization, radio transmissions, etc. So let's step back across all of the talks that we've seen today and look at what are all the precursor phenomena. And I was actually updating the slide in the back of the room with some of the other good talks that I saw earlier today. But this is kind of a broad summary, and I apologize if I might have missed your particular phenomena of pleasure up there. But these are the different phenomena that we've all been talking about. And at the bottom, I'll put down traditional seismometry, and I'm sorry for the USGS guys in the room, but I just wanted to put the new ones up at the top. So now let's think about, for all these different phenomena, what are the different indicators that we might be able to sense out in the world that might be able to show us what's going on with them? Well, here are a few. We've talked about radon emissions, air ionization, magnetic flux, groundwater chemistry changes. I'm not sure that we talked about today so much, but just a couple talks earlier, we were talking about animal-human behavior, physiology, tree potentials. There are many things that we could actually measure out in the real world, many of which are already being measured in different places with different systems. And those might be indicators that might indicate what's going on with particular earthquake phenomena, precursor phenomena. Okay, so here's the big picture. What if? What if we deployed a series of ground stations providing real-time multimodal sensor data? And Tom and the QuakeFinder guys, along with many other people in the room, have actually started to deploy those stations. What if we had access to all of those different sensor stations' data, real-time, together in one place? What if we also integrated remote sensing data from satellites and from many other sources too? So we could get the TIR imagery and look at, are there any other changes that happen that could be picked up by a satellite? And we're able to bring in all kinds of different satellite data too. What if we integrated all the existing seismic, ELF sensor networks and all those other sensor networks that are out there? I think we've all had different speculations of what might be a precursor or what might show up on what particular system. But I'm honestly even more interested in those that we couldn't have even predicted. What if we were able to integrate everything together into one place? And from my background in simulation modeling and analytics, what if we were then able to plot it in n-dimensional space and do principal components analysis and see what clusters, see what correlates together? The integration of everything in order to solve this problem. Because what I think you'll find is if we look at any one of the particular precursors that we've talked about and any particular indicator that anyone's talked about, we get a kind of fuzzy signal. And TIR, we get a fuzzy signal. And animal-human behavior, we get a fuzzy signal. What if we were able to integrate all those signals together so that the signal arises from the noise? That's where I think this gets really interesting. What if we were then able to fuse all the data together, visualize the result in real time, but most importantly, coordinate our actions worldwide to solve this? Around this room, you have experts in every particular precursor, every particular indicator that's out there in the world. What if we were able to work together and take all of those and fuse them together and have a multiplicity of our efforts instead of an addition? So, what I'm going to show you right now is one component of that. I actually have 3 surprises for you today. This is the first one, is my colleague Valerie Barker. We'll show you an earthquake precursor station that we're releasing here, announcing today. This is the only reason why we have this station is we're about ready to ship it up to Ketchikan, Alaska, and that will be significant in the second surprise that I'm about to show you. So, thanks for pausing. So what I'm going to do is let Valerie talk a little bit about the station that we've put together now, and what this is, just to take a second to give you the big picture on it. What we've done in IntelliSense is we've built a box that lets us plug anybody's sensor into the bottom of it. And we actually have a website called sensorexperts.com where we list thousands of sensors. So if any of you are developing a new sensor of any type, we can integrate into this box usually in about 2 weeks. The sensors we've happened to select right now that we're about to show you are ones that seem pretty reasonable at the time, and it looks like they very well might have been pretty reasonable. But the whole idea behind everything I'm talking about is collaboration. If you've got a better sensor, great. Let's talk about how we can share it and share that technology. If you've got a better satellite image, a better processing algorithm, great. So I'll get to all the details there. So why don't I turn it over to Valerie to explain a little bit about the station that you see in front of you, and I'll keep flashing up the detailed information on the screen.
Hello, everybody. It's nice to get out of the lab and play Vanna White for our global earthquake forecasting station. So at the heart of our global earthquake forecasting station is the IntelliCell, which Kevin just mentioned. This is our sensor platform. So it has a variety of interfaces, analog, digital, for many different types of sensors. We also have Ethernet interface, Wi-Fi, etc. And as you can see, with our global earthquake forecasting system, all of our boards are occupied by these sensors. Well, we also support wireless sensors as well using the XB format. So our data router actually uplinks data to our server, and that can be via cellular or satellite. And then when we deploy multiples of these stations, they act like a wireless mesh network. And this mesh network is self-healing, so if one of the stations goes down, data is automatically routed to our server gateway.
It's 10 to 40 miles between stations.
And it's 10 to 40 miles per station. We have several networks of these deployed in Hawaii, and they've been running for upwards of 10 years, doing environmental monitoring. So this is something that we're familiar with. So I'll go over the sensors. So at the top here, we have a weather station. So we get basic weather parameters from it. It has ultrasonic wind direction and wind speed measurement, as well as temperature, relative humidity, and rainfall, and all the standard weather station parameters. And then moving on, we have one of the most important sensors of interest for you guys here at the conference, the magnetometer. Of course, in a normal deployment, the magnetometer would be located away from these interference sources, just so I don't get called out on that later. Next, we have several gas monitors. So we're measuring ozone, sulfur dioxide, carbon dioxide, nitrogen dioxide. Whoa. Also, so these are all electrochemical sensors that we've interfaced to our system. And then behind here, which you can't really see, but you can come up later and look at it, is our air ion counter. And when these stations are deployed in the field, they're completely standalone. So we would add a battery pack and a solar panel to this. Actually, the couple of global earthquake forecasting stations that we have deployed now are running off of AC power because it's available.
Sure, okay, I'll dive back in. So we have a few other sensors that we're looking at deploying also along with this system. So you'll have EMF, water quality to look at water chemistry changes also that occur in deep groundwater, particularly cations and changes in turbidity that may precede an earthquake. Radon, I really want to talk to people about radon. I saw a poster out there I'm pretty interested in, but looking at other sensors too, whether we talked about. Also camera, being able to look skyward and look at lights is one other precursor people mentioned, lighting effects that change, as well as frankly for security and just a sense of presence. Here's the bottom line for it, is we built, the reason why we designed the IntelliCell, it was actually a spin out again from NASA, Ames, and Stanford, because what we saw was everybody out there and the brothers building new kinds of sensors. And then they all have to build some way of transmitting that data from anywhere. And then they all have to build the same backend. And when I was working directly for the DoD, we were funding lots of sensors, and each one we had to build the way to transmit the backend, and that cost millions of dollars. And then we would do it for the next sensor, and the next one, and the next one. And that was pretty silly. So the idea is, what if we built one box that just took care of that data transmission issue, and the backend, and had a free data storage, and all that sort of stuff. So that's essentially what we've done with this. So what you're seeing here pretty much is just the cost of all the different parts, and it's roughly about $30,000 right now. In volume, which is probably what the question is going to be, is we're looking to hopefully drop it even lower than that. Yes, quick one.
On the photo there, you've got an anemometer on there, which
Yeah.
makes me wonder, I mean, if you jazz this up with a couple of cheap weather sensors, don't you get a whole bunch of more people interested in deploying them for their own purposes?
Great, and the astute listener would have also noticed that, wow, are all of those gas sensors that Valerie mentioned, do we really need those for earthquakes? And the answer is no, but the same sensor station that you deploy for doing earthquake precursors, you can also use for doing things like carbon monitoring, air quality, and in fact weather. So we happen to like this weather station that we have up here. This is a Vaisala. It's very extremely robust in very rugged environments. We've deployed all kinds of different weather stations all around the world. Moving parts are bad when you put things up in very cold climates. They're very bad in marine environments too. They'll break down after about 2 years. This one, no moving parts. It's actually ultrasonic, so this is one we tend to use in those. But very good question. The same stations that we're deploying for this, you can use for lots and lots of other things. And that, frankly, makes it a lot easier to justify costs like this. Something else that's really cool is that, and I'll get to this in a minute, you can have students deploy these. It's a great student project. And then they get to go online and see the data. And they get to have own personal ownership and identity with that and be connected in with trying to save their own community, not just for earthquakes, but also with respect to air quality, weather, and gets them really involved in science from a deeply personal level. Does that answer your question okay? Yeah, cool. Okay, so that's the sensor network. And what we would love to do also is integrate in lots and lots and lots of other sensor networks data. But what about remote sensing data from satellites? Well, right now we're already bringing in the NASA MODIS satellite that you see here. We've also finalized our agreements with European Space Agency to get Meteosat, Swarm, and lots of their data, and we are starting to bring that in now. NOAA GOES satellite, and then high-resolution imagery we already have, rapid eye and digital globe as well. So within our system, we have lots and lots and lots of satellite imagery already streaming into it, both from NASA, European sources, and lots of other sources as well. As far as integrating other data, these are some of the other networks of data that would be pretty relevant. USGS's sensor networks, yeah, we're good with that. EMF sensor networks, and I want to really talk to someone about that today. And we already take in tweets and other information from human sources as well. And then there are lots of other systems that have been deployed also. But the big picture is this. What if you build a system that let you integrate all of that together into one place? Well, where do you go to get this? Well, it turns out that what would be really helpful is a platform that allows all of us to work together no matter where we are in the world, what organization we're part of. So we're about to publicly release a website called collaborate.org that lets people do that for any good purpose. In the context of this, though, what I'm doing is opening up the GEFS, Global Earthquake Forecasting System, portal on collaborate.org for anybody here that wants to join and collaborate and work together, no matter what organization, what country you're in, what your background is, where you're located in the world. If we can all work together, we can have something that will blow people away. And I'm firmly convinced of that. So all you need to do is to go on to gefs.collaborate.org, and you will see things like all of these collaboration tools up on the site. You will see a visualizer that, Google Earth on steroids. It's not Google Earth. It's much better than that. And working with Patrick and the Whirlwind team here and their visualization expertise, this is the box that all of their great technology goes into. Collaboration tools like video conferencing built in, so we can all do a bi-weekly video conference when we're not together in this room anymore. We can still work together. Here's all tweets in the world saying anything about earthquakes. Here's all RSS feeds in the world talking about any news having to do with earthquakes. These are data that's already streaming into the system, that, along with a bunch of other collaboration tools. The idea is, what if we had all those tools to work together and all of the world's data, satellite imagery, sensor data, everything, all in one place so we can really make a huge impact and work together. And yeah, that's your second surprise is, hey, you get access to it today. So let me wrap up here and then you get your third surprise. Here's a big picture, is really many phenomena have shown to be precursors. Individually, they don't really have that much predictive power, but if we integrate all of them together, hopefully that signal rises above. And although we don't really know how reliably they'll be able to predict earthquakes, if we integrate every crazy idea or scientific notion anybody's ever had about some precursor to an earthquake, integrate it all together, that might just be the system that might work. So, did this work? So, working with the Alaska school system, Kodiak's High School, Old Harbor, and with a great guy named Ron Fortunato at a group called Trillium Learning, we actually shipped a couple of these stations up to Kodiak, Alaska. Kodiak Island is right near Homer, just south of Anchorage. It's an island. And it's a volcanically active and earthquake active area. And so they actually deployed a couple of stations up there, and this station is destined to also go to Ketchikan, Alaska. Well, it turns out we got lucky. We deployed it up there, and not too long thereafter, they actually had you can't see it in blue here, but they had a magnitude 4 earthquake right there. And this is what we found out when we looked at it, at the data. Nothing, 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 nothing. Boom, 36 hours before the earthquake. Magnetometer went off. This is the z-axis, oh, sorry, this is x-axis. Also, you can look at the z-axis. We also got some other detection over here. The z-axis signal was, what was the value? It was 1,000 nanotesla. It was huge.
That's huge.
Yeah, blew me away. Frankly, I want to go back and double check the math. But it was very noticeable. What's that?
What was the time of the earthquake when you started?
The time of the earthquake.
Where was it when you started?
It was further out. I've actually got something I think that'll show that better in a moment. But basically, it was out there. This, again, preceded by about 36 hours. You kind of can't read it back there, but the dates are down here. But even better, if you go into that GEFS portal, you can see this data live. And let's look at it. And there's a also GEFS portal on collaborate.org, full open API. For those of you that like to program and hack, go to api.collaborate.org/docs. Full open API to connect in and get access to all of the data that I just mentioned. So all good for all of us. But anyway, just to cut to the chase on it, I think that it is time for us to double check all of the data because we've seen something, and it sure looks interesting, that preceded the earthquake. So again, the earthquake happened at November 13th at 10 p.m., and then you can look back at the data. We do everything in UTC, but you can also change the time zone. One of the other things that we started to do is we also started to, we read Luca Perotti's paper and a lot of the other papers having to do with TIR, and we started to take in that data. So this is one of your final surprises for today, is we started to take in all that data, and we are now processing the whole planet at 1 kilometer resolution, basically applying Luca's algorithm right now. And we started playing around with other stuff too. And that's why we love Luca, because we want you to work really hard and figure out what, I'll show you what we're trying to do. We're trying to figure out what distance behind temporal to average before we take the actual signal. We're looking at basically all the parameters around which you're doing, but you're the better guy to do that. We'd rather just implement what you find. Well, here's a couple of videos that we basically just created, some of which were created and uploaded in the last 10 minutes right before I walked up here. So this is the least interesting one. This is the whole Earth TIR, anomaly processing, and right before the Japanese earthquake. And we'll keep this loose. And again, we were using MODIS, so you'll see it's happening once a day. You'll see the sun go around. So this is before the Japanese earthquake, and we've overlaid what's happening here. And you see some glowing there, but again, that was more of a marine type earthquake. If I could, in the interest of time, let me go ahead and stop this and get to the one that's much more interesting. The thing that I had Joy, one of our engineers, do last night, actually this morning is when she ended up doing it, is to actually run this algorithm on the La Aquila area back in 2009. So right now we're processing every day. I've had her go back and do all of, I believe, 2014, and then I had her go back and also pick around the La Aquila area because I knew Luca was going to be here. So this is us trying to replicate Luca. What you're about to see is 3D, again, it's MODIS, so it's every night, 3-day average surface temperature, then subtract that from today, exclude anything within 5% of what that average is, and then color code it, orange to red. So this is a 3-day average. And when the timer gets to here, that's when the earthquake happened. So you see precursors here, you see the sun going around. And again, this was just shot, this was just today, a couple hours ago. So you see some glowing there, some TIR, some sort of anomaly. We do see also false positives in other areas that I'd love to talk a little bit about. Some other areas down south. But you do see glowing right before it happens. There is some sort of anomaly that, again, the ground's hotter than it probably should be. And then the earthquake happens, and then you'll see after that, seems like the anomaly starts to go away. But again, this is that 3-day average. So then the question is it better to do a 7-day, or a 3-day, skip 3-day, or what? And I can show those at the end if you'd like. Honestly, what I think would be really great is to do a Monte Carlo. Try everything and figure out what really works best. And frankly, it would be better to use a different satellite than MODIS. Like I think you're using Meteosat.
Or have a fleet of satellites.
Or have a fleet of satellites. And again, that's a part of the collaboration thing, is somebody else can make a fleet of satellites for all kinds of other purposes. I just love to get the data to do this. So that was, again, the 3-day average, anything above 5%. I'll show you a couple other ones. This was a 7-day average window. So again, slightly less signal, we thought. That's why I didn't show this one first.
And when on the timeline is the earthquake?
About the middle. We did 3 days before, 3 days after. But I think from Luca's papers, you went way back in time and you saw stuff. And again, we just had, just this morning to put this together. But this is the sort of thing you can do on collaborate.org really, really easily. So again, if everybody in the room that generates data, uploads that data, makes it available, then all those people that want to do the processing on it also can have access to it and visualize it. And I think, again, that we can make a much bigger impact. So this is the 7-day average before that, frankly, we thought would look a little bit better, but it looks like the 3-day average kind of produced a stronger effect. And I'm happy to give you copies of this afterwards where we can talk about it. And then one other thing that our engineer did was a 3-day average before the last 3 days, just seeing if that produced anything different. And again, that's one of the great things about this is you can just run this again and again and again. And we can overlay all the sensor data on top of it and anything else that we have in the area. And ideally, if we had animal behavior or anything else, you can start to lay all these on top of each other and cross-correlate and see what really comes out of it. So I think my time's about up. Let me just hit to the take-home message. Here's the bottom line. We're big into collaboration. We want to work with everybody. We've developed and deployed this next-gen sensor precursor sensor stations. They're commercially available. They're 30K. You can go to sensorexperts.com and you can order one right now. Realize we are upgrading the technology all the time. The magnetometer that we have here, we actually have an even newer generation that we're working on in the lab right now. This system detected something. I don't know what it is yet, but something happened 36 hours before a local quake on the magnetometer. And it was a strong signal. And frankly, I think because it was pretty close to where the earthquake happened. Maybe it's some ocean effect, I don't know. We can speculate all day long. But again, just jumping back to the big picture, I don't know, I'm not omniscient. I don't know what precedes earthquakes for sure. But I know if I integrate everything together and look at everything, I might be able to find something, right? So what if we integrate all this remote sensor data from satellites, existing sensor networks, et cetera, and that's what I want to do with everyone. Integrate everybody's data together, fuse this, visualize the result, coordinate our actions worldwide. And what I'd like to ask you to do is please, let's all work together. Join us all and let's collaborate. Thank you.
Thank you, Kevin. Sorry. Now you got a real, very, very strong presentation that shows what is the direction we can go and how much is already in place. We now need, well, we need the funding to put all the things together and to install many of these networks and integrate them with existing satellite and with satellites yet to be built and developed and launched. So, questions please, and also Thomas and, yes please, no, start.
Well, what's the business model? It's a good idea. I've done a lot of these things in my life. You have to think about business model,
Yeah.
how people subscribe, who gets, who pays for what, how do you utilize the information, and then if there are 100, sensors are there, 100 users are bringing information to you, how do you create weights for that information?
How do I create what?
Weights. Everyone has, all of them are not equal. All the information is not equally relevant, but we don't know. That's the question.
Weighting factors?
Huh?
Weighting factors?
Weighting factors, but we don't know what weighting factors should be
Yes.
yet, right? So if that's as simple as that, we would have known the answer. So we can talk offline, but I want all of us to think this very seriously, put it together, business model. If the economics makes sense, then all research makes sense. I'm a scientist. I'm also a corporate executive running companies. So I look at both.
Yep, cool. So let me hit on all those points. First, as far as the algorithms and analytics and weighting factors and stuff, thank you for volunteering. Nobody knows the answer.
Okay.
So the idea is get other people to be able to figure all of that out, and we'll all collaborate. We'll figure out what those weighting factors should be. That's the really cool and exciting research part. So yeah, I don't know it, but neither does anybody else. Let's collaborate and figure it out. As far as business model, yes, actually, we've thought quite a bit about that. Not just within the context of earthquakes, but also within the context of collaborating. And I could go through the whole spiel, it would take me a little while, but basically collaborate.org's got its own business model. This fits in really nicely with that. A quick version is the way that we build everything is based on a collaborative development model. Second phase of that is a very, very cheap subscription model to just pay for the servers. Third phase of that is access to data, premium data. We will never, ever, 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 ever sell anybody's data. It's your data. But there are other ways that you can make money to keep things sustainable also. In the case of global earthquake forecasting, I'll just leave you with this. What if we made a system that only was 1% accurate about predicting earthquakes? 1%, that's all I'll ask right now. Earthquake, multiply that by how many billions of dollars are lost in a major earthquake, let's say in the Bay Area, multiply all of that out, and it pays for itself right there. I think that we're going to be able to get
I understand the direction, I'm talking about.
So reinsurance industry, obviously insurance industry, et cetera. But maybe the final thing I'll end on is, if we keep working in our own isolated sandboxes of research, I'll be very controversial. Nobody in the real world appreciates or understands or cares. If we bind this together and say, guess what? We actually made a system and it predicted one. Doesn't mean it's perfect, but it predicted that one and they knew, and therefore we minimize the damage. That's huge, huge.
I'm not suspecting the goal.
Yeah. So the answer is yes. There are a series of business models, placeholder for a longer conversation. Yes, sir.
Hi.
I just need to point out, we do have a coffee break coming up.
Okay.
After the coffee break, we have a remote presentation from Louis Larson, who will be on the speaker, and we will present his. So whatever we discuss now would cut into the coffee break, because I want to be back here, that we all come back at 4 o'clock sharp. But
Well, also let me throw in, hey, during break, let's talk about sensor stations, let's talk about collaboration, collaborate, take you guys on there.
Right. And quick question, or then we can.
I think it's an important question, more important than a coffee break that people could leave for in the middle of my question if they want coffee that badly. Two things. One is 1% accurate, whatever the heck that means. As you know, or maybe you don't, when you're talking about prediction, and that's big business nowadays, not necessarily for earthquakes, but in all sorts of other fields, there's standard metrics for quantifying things involving false positives, false negatives, type 1, type 2 errors, all these different things. You have to, I think, be clear with this stuff. It also gets into this kind of file drawer effect and cherry picking stuff that's going on with these charts, where you show us these blotches shooting all over the screen and then say, see, it's an anomaly, and then we don't get to see what it's like during all the other times. So
I'm happy to show you all of the data, you can
Right.
download it.
And so then, fine, everybody knows what I just said. But what I'm about to say, maybe will strike a chord with some. There's a really big business nowadays. I mean, tens of millions, hundreds of millions are being poured into it. Every new company, big data visualization. And all these guys are going after this superficial stuff, like, what toys should we advertise on Facebook to you, and things like this. But this is a perfect example. What you're doing is the important part, which is getting the data. I'd say don't worry so much about principal components analysis. Let the machine learning and big data analysis people go to town on this data and see what they can come up with. And you guys, who know what are the right sensors and how to deploy this stuff, that's the important part. These big data people need to justify their existence on some higher level, in my opinion, than what they're doing to justify all these hundreds of millions that are being poured in by investors. And they might actually really go to town on this earthquake prediction problem.
So collaborate.org currently has over 2.5 million layers of data, sensor data, satellite imagery, social media, a database of other information. It's about 5 petabytes. I agree with you completely. We need to make this available for other people to do all that sort of processing. But what's different about collaborate.org versus Amazon or eBay or whatever, or Facebook, is this is for solving the world's really, really important problems. That's what the collaborate.org
Are
is.
these big machine learning companies and big data companies tapping into this resource to
Not yet. You have to realize, first you got to get the data, then you got to get the system to be able to process the data, then you can run the algorithms. And we're actually at that stage 3 right now.
Okay, one question. And such stations we have nearly since 20 years. I installed nearly 100 stations worldwide. So the main problem, nearly the same. I don't know that the power consumption is very low. I think you have a high power consumption with a solar battery in northern lands like Russia or in Kamchatka and so. I don't think that it works. Okay, maybe good. But the main problem, we installed more than 100 stations, more, but in different institutions. The main problem is now how we get all this data together so that we have it in a central place. The station is not the problem. This is the state of the art. This is very easy to handle. But the main problem is the collaboration between the different institutions. We can fit in the data format, also not a problem. But to bring them together from Taiwan, from Japan, from Turkey, from Italy, from Mexico, from US, and so on and so on. And this, I think, is the biggest problem. And the next problem is how you handle the anomalies, how you develop a strategy in the central computer or in the computer of the station, so that you know what is an anomaly and what is noise. This is the direction. And in this direction we have to collaborate very intensively, so that we understand this, so that we cooperate. To produce some station is today no problem. To bring this station in the network, in the international network, also to analyze the satellite. Where will be the center? Who will understand? Who will inform? This is a very difficult problem. You need national centers, you need international centers to control it, like we do it now with the seismicity. So the seismic signal is going several hundred kilometers, but the geochemical signal, it's going only 5, 10, 15, 100 kilometers. It depends. It depends on the strength of the earthquake.
So you touched on the key reason why we built collaborate.org is people need to work together for some of these big problems. Earthquakes, pandemics, climate change, these things that require more than one individual, organization, agency, or even government to handle. And that's the whole idea behind Collaborate. So I agree with you completely. And also I agree that after you figure out that you might just have a system that's reasonable, you really do need to work on policy.